All right. So I will talk today how you can break the communication bottleneck in your SDV stack with iceoryx2. And these slides are based on true stories from 10 years of working in SDV. And it all started with a glorious vision, blooming landscapes. Because we are now moving from small ECUs to big vehicle computers, many cores, plenty of memory, real operating system. So good days for SDV developers. So now let's make this vehicle computer the sink of all data and then the source of all power. So let's connect all these ECUs to Pöhnl ECUs, which are then the CAN to Ethernet gateway, and stream all this data into the vehicle computer. I've seen projects that had 50 to 70 sockets to get all this data handled by 50 to 70 threads. Then you can say, okay, we go the next level of autonomy. Let's have radars and cameras, lidars, ultrasonic, all connected to this vehicle computer. And we can rethink how we deploy software. So on the left-hand side, you see how it was done on OSEC, where you have a single address space operating system and compile everything into one binary. So you have tasks and you execute chain of software components one after the other. But with SDV, we could make every single component a known process. So I've been talking to people who said, why should I switch to POSIX if I'm not having every single component in its own process? Teams can work independently. Someone even said they can use different versions of the same library. And have this all separated. You can update them separately. And as you want to have some execution order of all this, you can introduce an orchestrator that then wakes up all these components and different processes at the right point in time. That's also how it's done in Eclipse S-Core, for instance. Then we want to go away from signal-based communication to service-oriented communication. So let's make every signal and service. A service would then be an ARACOM event or some IP event or DDS topic. And if we have every single known service, we can have a lot of flexibility in how we distribute all this information. But then reality hit hard. Because if you have a lot of legacy software components, a lot of new components, all integrated on this new wheel computer, you will have a lot of software components. If all the software components are separate processes, you will have a lot of processes on POSIX. If you collect all this data from Pöhnl ECUs and sensors, you will have a lot of inputs. And if every signal becomes a service, you also have a lot of services. And all this data transfers now are between processes. So you have a lot of inter-process communication, or short IPC. And this is how data passing between software components used to be on OSEC. You have a single address space, so one component write data into a global memory. Another component can just read the message. Very efficient. And if these components are running in different tasks, maybe you have to do a single copy, which is typically small data, so also don't care. And quite efficient. This is how it looks like on POSIX. Now the components are in different processes. And you want to have some abstraction. You don't want to directly interact with this operating system APIs. So you introduce a middleware. And data passing from one component to the other more goes like that. You write a message. You pass it to the middleware. This serializes the message. Then takes an OS IPC mechanism to transfer the message from one process to the other one, which means you copy it in and out of the kernel. Then you wake up a thread that deserializes the message to then maybe wake up the next thread to execute a callback where you process the message. So all this comes with a lot of serialization and copies and context switches and user kernel mode switches. And this comes with a price. And people started to realize that it doesn't really scale. And There are a lot of projects where people had to fight with overload, delayed SOPs, because real computers are often just bigger ECUs. I've seen real computers with 2 cores running Linux, or 4 cores, but then have a hypervisor and run Linux and QNX in parallel. So it could mean you have only 1, 2 cores to run hundreds of processes, hundreds to thousands of threads that are all competing on these few cores, thousands to 10,000s of IPC data transfers. And as I just presented, data transfer comes with all these copies and context switches and syscalls and so on. So there are 2 dimensions where you could get scalability limitations. The first is the message rate. So many of these middleware solutions trigger a callback to process the message. So every time you receive a message, you will have a context switch and execute a callback. And then you often have additional threads inside your middleware that are also involved in this message passing, so you have additional context switches there. So this means if you have like 10,000 messages per second, you will have tens of thousands of context switches per second. And I've seen systems where we had more than 50,000 of these context switches per second on a single core. And there are certain boundaries where it just starts hurting. The next dimension is the message size that gives you trouble. So if you have all these copies and serialization in the middleware stack, this comes with CPU cycle, and this also comes with latency. And the bigger the messages, the more CPU usage and the higher the latency. So here you see a measurement on a Raspberry Pi for the IPC mechanisms that are coming with POSIX systems. Typically, it's a message queue and a Unix domain socket. And you see that with 1 megabyte message, you already have roughly 1 millisecond of latency. This is now a real-life system. It actually runs iceoryx. We have an autonomous driving based on an end-to-end AI model, and it takes 6 high-resolution cameras, 35 megabyte per image, 20 frames per second. So just this data stream from the camera is about 4 gigabytes per second. Now think, you copy this data on the sender side, you copy it on the receiver side. Maybe you want to have some recording with the next process, so you'll have additional copies there. So it's quite easy to end up with 10 to 20 gigabytes per second just for this small subset of your system. Consequence, high CPU load and high latency. So that means, unless you're currently performing a context switch, you're probably copying some data. And you do not really have a lot of runtime for really doing your workload in your SDV stack. So does this mean it's over SDV? Or is there a way out? So for me, the communication overhead in your system can be described by this equation. It's the system decomposition divided by the middleware efficiency. Sure, the higher your middleware efficiency, the lower your overhead. But you also have to be careful with your system decomposition. The more processes, the more data connections, the higher the overload will be. I'm not saying that decomposition is bad. You should have a clean architecture and separate things. So decomposition is a good thing. But you can also do over decomposition, and then it gets expensive. So you should be careful with your architecture. Then iceoryx2 will take care of the rest. So how? iceoryx is an inter-process communication technology based on shared memory. It was started in 2015. We also then took the ideas to the standardization of AUTOSAR Adaptive, ARACOM, API, and ROS2 to ensure that you can have efficient communication based on shared memory in these frameworks. It was open sourced in 2019 as Eclipse iceoryx. And in 2023, we started iceoryx2, which I will talk about in a minute. And With all the teams working on iceoryx over the past 10 years, we could say that's based on more than 70 years of combined experience in developing high-performance inter-process communication. How this works on a high level, you have two processes, a sender and a receiver. iceoryx creates some shared memory that's mapped into these processes. This allows you then to, on the sender side, write the message directly into shared memory. On the receiver side, read directly from the shared memory. So you can have the same efficient message passing that I showed you on OSSEC operating system. But iceoryx then provides a whole communication infrastructure around all this. So the entities for sending and receiving data, their discovery, connecting them, whole data delivery, all this memory management, memory synchronization, it's all then handled by iceoryx. And as you then can pass a message from one process to another without a single copy, we call this true zero-copy communication. And over the past few years, it became obvious that if you have a data-intensive system like autonomous driving, that's a must-have technology. So most frameworks out there that are proprietary open source either integrated iceoryx or were inspired by its ideas. And it's great to have such a technology in open source because it's a common problem across many different industries. And if you have an open source solution, you don't have to reinvent the middleware wheel here and can just take a robust open source solution that does the stuff for you. So now we talk about three properties that make iceoryx2 a solid foundation for your SDV stacks. First, it's the efficiency. So with this true zero-copy inter-process communication, we can pass the message without a single copy. And this gives you a constant sub-microsecond latency. And the good thing is, independent of the message size. So here we have the same measurement again on the Raspberry Pi, which is comparable to automotive hardware, more comparable than your laptops. And for small message sizes, it's not that much of a big difference. But if you think of megabyte messages, it's more than 1,000 times lower latency. So think of below microseconds and not above milliseconds. This then enables dozens of gigabytes per second with ultra-low CPU load. And also, the lower latency enables faster reaction times from sensing to acting. And you save a lot of workload, so you can have smaller, cheaper CPUs for the same workload. Or what's also crucial, you can go embedded without going crazy, because typically then you get problems if you want to move from your pre-development machine to an embedded target. The second property is determinism. So iceoryx2 comes with no internal threads, no syscalls in the data delivery path, no hidden blocking calls, no heap allocation during runtime, no central daemon, no surprises behind the scenes. There's nothing happening behind the scenes that could disturb your application. So this enables, together with this low latency that we have with the zero-copy communication, minimal jitter. And this is important for predictable execution and if you want to realize some real-time applications. So here in this figure, we see on the left-hand side how an interference with middleware thread can lead to latency spikes. On the right-hand side, we see if there's no interference with such middleware background threads, you have a stable lower latency. And for sure, if you don't have threads inside your middleware, you also have less scheduling overhead, which means lower CPU. The third property is flexibility. iceoryx2 is written in Rust, but it already comes with language bindings for C, C++, Python, and C#. And it runs already on a bunch of operating systems, Linux, Windows, macOS, QNX, few more, even bare metal. And we have different messaging patterns. So we have many-to-many publish-subscribe communications. Think of some IP events. Or internet-style regress response. Think of some IP methods. A key value storage that has a key value storage implemented in shared memory. We call the blackboard pattern. And we also have an event mechanism that allows you to have data-triggered execution either for data-driven execution, or you could also use it for sending small efficient events for having time triggers across different processes. And we also have per receiver queues with configurable sizes. And one important aspect is that we can configure the overflow behavior of the queues. So either you say, if I have a queue overflow, that's an error I return, I drop the new message. You could say, I'm blocking the sender, I'm waiting for the receiver. Maybe not the best for real-time and safety-critical systems. And my favorite is we have an overflow and drop the oldest messages. So here we can have the latest, greatest messages stored for you in the background, very efficient with best memory efficiency and lowest overhead. Additionally, we have historical messages, so you can have late joiners that get already data sent in the past from the senders. Here on this figure, you see a small example. We have a fusion node. It has different inputs from different sensors running with different frequencies, and now you can configure iceoryx to say, okay, for my LiDAR sensor, I'm only interested in latest, greatest. So every time I want to consume some data, I have the latest LiDAR scan. For my camera, I want to store up to 4 camera images. But if it's get older, I'm start dropping old images and replace them with new ones. Or you say, I want to have all the messages. I configure the maximum queue size and treat an overflow as an error. More technical details into all of this can be found in my FOSDEM talk that I linked here. And iceoryx2 already surpasses the first generation, which we now call iceoryx Classic, when it comes to features, when it comes to GitHub stars, and it's already used in many different industries. So it's running in leading simulators for automotive, automated driving, all kinds of robots. It's used for high-frequency trading, industrial cameras, different medical devices up to surgical robots, maritime, avionics, drones. So everywhere we have a need for low latency and high-volume data transfers. And we also have a lot of synergies within the Eclipse ecosystem. The most obvious thing is to use iceoryx as an IPC layer in a bigger communication or framework stack. So we have IPC plugins for Cyclone DDS for both iceoryx Classic and iceoryx2. We have an IPC plugin for Eclipse eCal. We have an IPC transport for U protocol. And it's also used in OpenSOVD and in SCore. And we can also connect different systems running iceoryx with a Seno tunnel. That's all. Questions?
Thank you. Any questions from the audience? Because I had a few questions regarding compatibility, and you already answered them basically on the last slide. Yeah, Kai?
Thank you. It's really great to see these, all of these projects using iceoryx2. Regarding the last 2 of them, I was wondering if I did not get the notice or if that is really true. To my knowledge, it is not used in SCore.
Yeah, but if you search GitHub, you will have quite some hits.
Okay.
So I guess it's not used everywhere in full detail, but the iceoryx Rust crates are integrated in OpenSOVD and in SCore.
Even better.
Yeah.
Cool.
So there must be something that's used.
And regarding U protocol, we had actually had a workshop, a full-day workshop with you and some of your colleagues discussing how it could be used as a transport in U protocol. So far, we're not 100% sure if the use cases are overlapping enough for it to make much sense. But it certainly could be used, but we're currently still discussing whether we actually want to use it there. But in any case, it's fantastic technology. I can highly recommend it. So whenever you have such a use case, you should really use it.
And you were the mentor back in 2019.
Yeah, absolutely. Yeah.
Wow. Okay. Do you still... Okay. There's a question... okay.
Hi, Michael. Here's Michael. Since the beginning, I was curious when you show the shared processes where you map basically the memory inside, are you using any semaphores or ways how to avoid any media collisions on writing and reading?
No. So we do all this reference counting behind the scenes. So you send a message. This means you push a pointer into a queue that's in shared memory, a log-free queue, and then this memory is in the end blocked until it gets free again because no one is reading anymore. And with the atomic operations that you have in this log-free queue, you're also synchronizing the memory. And then it depends on, do you want to get woken up if there's a new message or not? And this is where we separated the mechanisms with iceoryx2. So the normal data delivery is just pushing into the queue. And then we have this event pattern where you can say, okay, if I'm sending a message, I'm also sending an event, which could be a semaphore or a message on a Unix domain socket, which actually then triggers the receiving process to wake up and consume.
Thank you, Michael.
Let's go to Phil. No.
Can I use it in functional safe context?
So the whole architecture is made with mixed criticality and functional safety in mind. We're also using the bleeding edge of the technologies that you have in Rust with Clippy and Myri for all this testing and stuff. Sure, for Rust, there's still a bit of way to go to say I have my ASIL system with Rust, but we already have the certified Rust compiler and so on, and people are working on a tool qualification side. What we currently do not provide is having all the safety artifacts in open source. Because that's also must be a reason or something that earns us the money and let us get something to eat on the table. But yeah, it's already used by companies that need safety, and yeah, we have all the artifacts then if you want to use it in such a context. But even compared to the iceoryx classic version, it's the next step also on having everything already in open source to check things off.
Thanks, Michael. I briefly want to touch base on the score used in score part. And basically because we had this question this morning where, here. We had this question this morning from the virtual audience where they said, like, what about the other projects from Eclipse? How does it integrate? How do we prevent of creating a platform and all these kind of things? And basically with iceoryx2 being mentioned, as you say, where you can search for in GitHub, even if it was not made with the score tooling, it can serve as a base, so you can replace certain parts, you can extend existing parts, and nothing prevents you from doing this kind of tailoring. And I guess that's the way how you get in then iceoryx2 as part of score, even if you don't find it in the score repository. So I think it's not really a question, but it's more like, say thanks for bringing this in and showing the flexibility which it provides. Yeah,
there are kind of variants of score where iceoryx is running.
Okay.
So it's part of the fixed execution order component and module within the score project. So this is where it's in and where it's located, just to say it out loud once.
Yeah.
It's used by the fault handler in OpenSOVD.